Here comes a demonstration of a Maclaurin polynomial for the function 1 over x minus 1 cubed. I'm not going to specify whether it's going to be 3 terms, 4 terms, 5 terms. We'll just develop the general representation, and then you can pick however many terms that you want. You may be wondering why I have the formula for a Taylor polynomial on the screen where I'm asking for a Maclaurin polynomial. Well, remember that a Maclaurin polynomial is a Taylor polynomial. It's just the specific case where the anchor point x0, which goes in 2 spots, is equal to 0. So we do need this. In this formula, the summation sign is hardwired. The n factorial in the denominator is kind of hardwired. This term is hardwired, and again with Maclaurin series, we will put in a 0 in the spot for x naught. The only thing that varies from function to function is that numerator there, which means we need to generate a list of derivatives of our function with 0 plugged in, and we have to do as many as we need to find the pattern so that we can write it down. So I'm going to make a little chart. I'm going to delineate some attempts, and we'll go as far down that list as we need, and farther if we need to. I'm going to write down the nth derivative of the function, and then we're going to plug 0 into that nth derivative. Now the function is also known as x minus 1 to the negative 3. So we'll think about it like that to make the derivatives roll out a little bit more easily. Now the zeroth derivative is just the function itself. And when we plug in x equals 0, we're going to get negative 1 to the negative 3rd power, which is negative 1. And then for the first derivative, well, we'll drop down that negative 3. Then we have x minus 1 to the negative 4. Technically, we multiply by the derivative of x minus 1, but that's just 1, so who cares? And then we go over here and plug in 0. 0 minus 1 to the negative 4 is just 1 over negative 1 to the 4th. So when we plug in 0 for this part of this term, that's just going to be 1 multiplied by negative 3. The second derivative, well, let's drop down the 4. So now we have 4 times 3 times x minus 1 to the negative 5th. I'm not going to multiply 4 and 3 and exchange it for 12 because I want to see every little bit so that I can see what pattern is rolling out. When I plug in 0 for this, negative 1 to the negative 5 is negative 1, so this will be negative 4 times 3. Third derivative, bring down that negative 5. Again, not writing the full product, just leaving it as a multiple to see the pattern. I think we've got the pattern at this point, right? That's a 4 times 3. Plugging in x equals 0 here, that's an even power, so this will get us a 1, negative 1 to the negative 6th. So the result, negative 5 times 4 times 3. So every term is negative. Here, let's take a crazy guess. Let's not even write the derivative. Crazy guess, the next result here, I bet it's going to be negative 6 times 5 times 4 times 3. Okay, we've got it. So when we roll these things together into a general formula, well, every term is negative. So negative 1 times, it's not negative 1 to the n or something like that, it's just flat out negative 1. And then let's take a look at the pattern that's developing here. This and this and this, they almost look like factorials, right? Well, this would be 6 factorial if there was a times 2 on the end. This would be a 5 factorial if there was a times 2 on the end. This would be a 4 factorial if there was a times 2 on the end. So it looks like every one of these things is a factorial that's been divided by 2. Which factorial is it? Well, for n equals 2, we're looking at something like 4 factorial. For n equals 3, something like 5 factorial. So that looks like, altogether, n plus 2 factorial. Okay, so that's the general formula for this numerator. So I'm going to go ahead here and write down, I'm going to call it capital M because it's now a Maclaurin series of order whatever. And this is going to be a sum for n equals 1 to, well, however many. And our coefficient coming from the derivatives, there's a negative 1 times n plus 2 factorial divided by 2. And then inside that denominator, I'm going to also include this division by n factorial. That'll just go along right there. And then finish it up with x minus, well, 0, because it's a Maclaurin series, to the n. And get rid of that. And simplify. So this is just, let's see, this will just be x to the n. This negative 1, we're just kind of stuck with it. N plus 2 factorial over n factorial. N plus 2 factorial is n plus 2 times n plus 1 times n minus 1, etc. So the n plus 2 factorial, we go down 2 terms, then we get to n factorial, and that's just going to cancel with the n factorial underneath, and there we go. So here is your Maclaurin polynomial for that function. If we want the 5th order Maclaurin polynomial, oops, I'm sorry, I started my index at the wrong number. Dang. Ooh, it was wrong on this too, wasn't it? Oh my gosh. Now it's better. Okay, that's fixed. So if you want, say, the 5th Maclaurin polynomial, well, crank out terms and you get to x to the 5th. And then let me show you what we just developed. This is a screenshot from Maple. The curve that you can see is red right here, and then comes down here and blends with the blue curve. This is our function 1 over x minus 1 cubed, the red curve. The blue curve is a Maclaurin polynomial going out to the x to the 5th term. So the anchor point here is x equals 0, right? There's x equals 0. Let's go down, find the function. We're right there. That's the thumbtack that holds these two things together, the function and its approximation. So the red curve is the function, the blue curve is the approximating Maclaurin polynomial, and you can see that in a region around x equals 0, the agreement is pretty darn good. Say there, and actually all the way down here, it's really good. But then over here at about, I don't know, negative a third, negative a half, the polynomial says never mind, and it just kind of flies off to nowhere, whereas the function keeps trending this way. And so a bigger question might be that we're not ready to answer. Well, if we added on 10 more terms, would the agreement spread farther in this direction, or is there some wall that gets hit around here where the polynomial just is not going to be able to match the function anymore? It turns out the latter is the case. Probably more information than you want, but this function, 1 over x minus 1 cubed, has an asymptote at 1. So there's an asymptote for the function right here. That's why both are heading down. So the anchor point is 0. The approximating polynomial is going to match the function 1 unit to the right, and it will lose its ability to match at that asymptote because the polynomial can't go across the asymptote. The polynomial can't have a discontinuity at that same location, which means, but there's going to be a symmetry here that that same distance on the other side is where it's going to be able to do the approximation. So from here to here till we hit the asymptote, which means on the left from x equals 0 at most to x equals minus 1, we'll see agreement. So if we added more terms, the agreement would get better towards negative 1, but it wouldn't go past that.